we've seen how to correct non-words of English, but what happens if the error produces a real word? This turns out to be a very common problem. Maybe between a quarter and a half of spelling errors, depending on the application, turn out to be real words. In these examples from a classic paper by Karen Kukic, the word minutes is misspelled as minuets, perfectly reasonable English word. The word and is misspelled as the word an, a very common English word. Leave as lave, buy as be, and so on. So these are, not only are these English words, but some of them are quite common and frequently used English words. So a much tougher problem solving the real word spelling error task. Again, what we're going to do for the real word spelling error is very similar to what we did for the non-real words. We're going to generate a candidate set which includes the word itself and all single letter edits that produce English words, and maybe we'll also in some versions include words that are homophones that sound alike. And given this candidate set for each word, we'll choose the best candidates, either using the noisy channel model, or you can imagine we'll talk later about more complex models that use classifiers. So let's look at that in detail. Given a sentence with word 1 through word n, we're going to generate for each word a set of candidates. So for word 1, we have the candidates word 1 itself, and then a bunch of variants, the single edit distance neighbors of that word. Word 1 prime, word 1 double prime, word 1 triple prime, word 2 prime, word 2 double prime, word 2 triple prime, and so on for each of the words. So we have a whole lot of candidates for each of the words. And now we're going to choose the sequence, capital W, the sequence of candidates that has maximal probability. In other words, we might pick word 1 from this candidate set, and word 2 prime prime from this candidate set, and word 3 prime 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 from this candidate set, and so on. For each word, we're going to pick some candidate, which might be the word itself or some correction of that word. And we're going to pick the sequence that is most likely. Let's look at an example of that. We have the, imagine the 3 words, the mini sentence, two of thou, T-H-E-W, thew. So for each word, the word to, the word of, and the word through, we generate potential corrections, each of which is a word of English that is edit distance of 1. So I've shown some here. So to could have been the word to if the original word to was the error was an insertion of a w, or it could be in the word tau, where the error was a substitution of a for w, or it could have been the word to, substitution of an O by a W, or it could have been correctly the word to could be correct. Similarly, of could have been the correct word could have been off, and there was a deletion of an F. So again, 3 candidates, off, on, and including the word of itself, and the word thew, which is a real word of English, could have been the word through, and the R got deleted, or the word thaw, or the word the. A very common word, and EW, a very likely error, it turns out, because W is right next to E in the keyboard, and so on. So we have each of our candidate sets, and then we just want to ask, of all the possible sets of sentences produced by paths in this graph, so here's one, to of through, here's another one, to on thaw, here's another one, to of the, and so on. For each of those possible sentences, what's the most likely one according to the noisy channel? We'll pick the most probable one according to the noisy channel. And hopefully the noisy channel, a good noisy channel model will pick the correct answer, to of the, as our most likely sequence here. In practice, for spelling correction, we often make the simplification that we're only seeing one error rather than letting every word have a possible error in it. In other words, the set of sequences we consider is the sequences in which only one of the words is an error and the rest of the words were correct as typed. So here, word 1, word 3, and word 4 were correct as typed, and it was word 2 that was misspelled, and we replace it by word 2 double prime, let's say. Or in this sequence, it was the word 3 that was misspelled. Thew was misspelled as the was misspelled as thew, and so here's the error, and these 3 words are correct, and so on. So this smaller set of possible candidate sequences. So instead of having to consider n squared possible sequences, we're just considering a constant times n possible sequences. From this set, now we choose the sequence that maximizes, that has the maximum probability. So we picked the most likely, most probable, conditionally most probable set of sequence of candidates. Where do we get these probabilities? Again, the language model, just as we saw before, we have our unigram, we have our bigram, we can use whatever smoothing method we'd like. The channel model is just the same, again, as for the non-word spelling error correction. The only difference is we now need a probability of having no error, because of course we're assuming that only one of the words is an error. So we have to have a probability for all those other words that are not an error. We need to be able to decide when we have an error and when a word is in fact correct, meaning that the probability of the word itself, given the word, is high, so unlikely to have an error. How do we compute this probability of no error? What's the channel probability for a correctly typed word? And this obviously depends on the application. And so we might make the assumption that in a particular application, one word in 10 is typed wrong, and that means that the probability of a correctly typed word is 0.9. Or we might have instead the assumption that one word in 200 is wrong, and so now the probability of any word being typed correctly is 0.995. So there's our channel model probability of a word not changing. Let's assume that the channel model of a task is has a probability of 1 in 20 of an error, meaning that 95% of the time a word is correct as typed. So here's an example from Peter Norvig. Again, we have the spelling error THEW. We want to know whether it should be the word the word thew, correct, that it was correct as typed, or thaw, or through, or thwee, and so on. And again, for each one, we generate our channel model, and the channel models were exactly computed the same way as before. We have the probability of a substitution of an A being substituted by an E, or of an R being deleted after an H, and so on, that we can compute just from our channel model. So here's our channel model probabilities. And again, we have our language model probability just as before. And so these are examples that Peter Norvig computed from the Google Ngram counts. And again, we've assumed the channel model of a word not changing, of the error X being generated by correctly generated by the word X. And we can multiply these together, that multiply together the channel model with the language model, and again, showing you things multiplied by 10 to the 9th to make them easy to read. You can see that the word the is correctly chosen, very high probability, as the misspelling of the word thew by itself. And in context, this is using a unigram language model. If we're using a bigram or a trigram, we're even more likely probably to be able to distinguish when the word thew really was the word thew and when it was the word the. So that's real word spelling correction. We simply take the standard algorithm, noisy channel algorithm for non-real words, add a probability of an edit not happening, and then allow every word to imagine every word could have been an error, and then look for the most likely sequence, simplifying usually by assuming only one error per sentence.